Welcome to Easy Tech. I'm Dr. Gayatri. Now I'm going to take you all with the topic on energy of a particle inside one-dimensional box. This topic also covers eigenvalues and eigenwave functions. So let's start with this. While starting with this equation, recall with the previous video wherein you have learnt about time-independent Schrodinger wave equation. So the application of time-independent Schrodinger wave equation is to calculate the energy of a particle inside a one-dimensional box. So here, consider that you are having an electron. This electron is trapped inside a metal. It could be trapped inside a metal, or you can consider that it is inside a one-dimensional box. Anything it could be. Suppose that the length of that particular box or the length of the metal that you have considered is A. You have considered here a metal, or it could be a one-dimensional potential box whose length is treated to be A. Now you are having here an electron or a particle to be trapped inside it. So when this electron which is trapped inside it is moving, you are having here the potential to be remaining constant. For time being, for simple calculations, we are assuming that it is equal to 0. So as long as it is moving within the potential box, that is between the ends 0 to A, its potential is assumed to be 0. So I write here the condition that V of x is equal to 0 for 0 less than x less than A, which means that the particle is lying between the boundaries 0 and A. And you are having the potential to be equal to infinity, outside the box. That means when the particle is lying here, which is less than your 0 and which is greater than your A, either less than 0, which means that it has not entered into the box, greater than A, that means it is out of the box. In any of these situations, the potential is considered to be infinity. So I have here for x less than 0 and x greater than A. In these two situations, we have the potential to be infinity. But within the box, you are considering that it is equal to 0. So now recalling with your time independent Schrodinger wave equation, dou square psi by dou x square plus 2m by h cross square into E minus V psi of x equal to 0. So when you recall with this particular equation here, this V is representing you the potential. So in place of that V, use your first condition V of x equal to 0. In such a case, the equation reduces to dou square psi by dou x square plus 2m by h cross square E psi of x equal to 0. This equation is rewritten assuming your 2m by h cross square as k square. Dou square psi by dou x square plus k square psi of x equal to 0. Where k square is represented as 2me by h cross square. Now here, this is a second order differential equation in the variable psi. So you will be having here the solution for this second order differential equation to be given as solution for the equation is, since it is a second order differential equation, you have two constants a and b, a sin kx plus b cos kx. Since this is the expression in the variable psi, here the solution is for the wave function psi of x equal to, this is the solution. Now let's look at the diagram. Here these are the two positions. the boundaries 0 and a. At the boundaries, we know that the wave function vanishes. That is, our psi of x will be equal to 0. Either if you consider it point 0 at the first boundary or at the end point A, at these 2 points, the wave function will be vanishing. The wave function becomes equal to 0. So now we are going to use those boundary conditions. So the condition is at x is equal to 0, which is the first boundary there, the wave function is 0. In such a case, the equation here reduces to a sine 0 plus b cos 0 will be equal to 0. We know that sine 0 is 0, so I'll write it as 0. Cos 0 is 1, so I'll write it as b. 0 plus b equal to 0. That implies constant b value equal to 0. Now we will go for second boundary condition. So if we look for our second boundary condition, it is happening at x equal to a. At x equal to a, the wave function is once again vanishing. So you are having psi of x to be given as 0. So if you are using x is equal to a in the above expression once again, you are having sine ka along with the constant a plus b cos ka, which is the second term, will be equal to 0, because at x equal to a, once again the wave function is vanishing, which is represented as 0. But we know that b is equal to 0. Here we have already given b equal to 0. So use the same. Then you will have a sine ka to be equal to 0. From this expression, you are having either a to be equal to 0 or sine ka to be 0. But a is not equal to 0. Since it is a constant, a is not equal to 0. Then what should be 0? Sine ka should be equal to 0. When do we have our sine ka value as 0? It is simply like our sine theta 0. When can we have our theta value? For what values of theta our sine theta is going to become equal to 0? For ka equal to plus or minus n pi. So from this expression, what will be our k value? Plus or minus n pi by a. But already we have seen in the previous case that our k square value is given as 2 me by h cross square. But now our k square value is n square pi square by a square. So we need to equate both of them. So you are having here k square equal to n square pi square by a square, and this is equal to 2me by h cross square. Already I have told you in the previous session that h cross is equal to h by 2 pi. So if you are substituting that, h cross is h by 2 pi, it becomes 4 pi square. So you are having an LHS n square pi square by a square. So if we are taking with that, pi square is cancelled on either sides. Then what will be left for us? N square by a square to be equal to 2me by h square. The same expression could be still modified to write the value of energy, which is given as E equal to n square h square by, we are having h square onto the other side and your 8m onto the other side, n square h square by 8m a square. So energy of nth level is represented as we can never have your n as 0. If n is equal to 0, then we do not have the possibility which gives you us with the wave function. So it means that n can never take the value 0. N will never take the value 0. So we are going for the next, that is, if n is equal to 1, if your n is equal to 1, then what will happen? E1 equal to h square by 8m square. As I said, we cannot have your n as 0. So it becomes E1 equal to h square by a square. This is representing you ground state. Then first excited state, E2. Then it is given as 4h square by 8ma square. But already h square by 8ma square is E1. So I can also write it as 4a1, which is the first excited state. Then go for the next, that is n equal to 3, which represents 9h square by 8ma square, which could be written as 9e1 representing second excited state. Like this, we can have number of energy states or excited states to be represented. The difference between any two energy states could be easily calculated. Generally, you can expect numericals with the difference between two excited states given as between a ground state and first excited state or second excited and first excited states, etc. Then it becomes E3 minus E2 or E3 minus E1 if it is between second and ground state. Like that, we can expect numericals based upon the formula En is equal to n square h square by 8ma square. So you are having here n to be given different values, and this we are going to have here to be called as possessing discrete energy levels. For every permitted energy, for every permitted energy, possible energy, allowed energy, we are going to have eigenvalue. The value you get is simply called as eigenvalue. For every permitted energy, we are going to call that energy level to be possessing eigenvalue. And you are having this n to be representing the principal quantum number. This is about eigenvalues or energy of a particle in one-dimensional box. Continuity for this topic, calculating the wave function and eigenwave function, we will look in the next video. Thank you. Like, subscribe, and share Easy BTech.